78% of government infrastructure maintenance is purely reactive. Public works departments across the country are effectively waiting for assets to collapse before they move to fix them. In high-voltage systems, that delay leads here, a catastrophic arc flash that destroys the equipment and endangers everyone in the building. This destruction begins with a physical shift. In industrial switchgear, constant mechanical vibrations slowly loosen the heavy hex bolts that secure electrical connections. This triggers the principle of Joule heating. As the bolt loosens, a sub-millimeter gap forms, forcing the electrical current to compress through a tiny point of contact. This creates electrical resistance, and that resistance strictly forces heat output upward. This microscopic heat anomaly escalates silently in the dark. It builds over weeks and months, deep inside the cabinet where no human can see it. Most facilities manage this risk with manual thermal scans, but they only do it once a year. This creates the calendar illusion, the belief that a single checkup can account for the mechanical failures that ignore our schedules. If that deadly resistance begins to build the day after your annual inspection, you are blind for the next 364 days. You're simply waiting for the flash to happen. To eliminate those blind spots, engineers are now embedding continuous AI microthermal sensors directly inside the high-voltage cabinets, locked onto the copper busbar joints. Because every physical object emits infrared radiation, these sensors can monitor the thermal profile of the equipment 24/7 without human intervention. The software logic is trained to detect a 5-degree deviation from the baseline. It identifies the heat anomaly the moment it begins, providing a warning long before there is any physical smoke. This data flows into a computerized maintenance management system. The AI bypasses human analysis to directly generate a prioritized work order based on the severity of the heat. A technician is dispatched immediately to tighten the specific bolt the AI identified. They apply the exact physical force required to restore the connection. This mechanical tightening restores physical continuity, halts the resistance, and defuses the arc flash before it can ever ignite. This predictive framework, moving from a sensor to an automated repair, scales across an entire city. While switchgear uses thermal sensors, the same logic applies to water mains using acoustic data, and it applies to HVAC systems using vibration patterns. For cities managing massive infrastructure, the transition follows a 90-day roadmap. Step 1 maps highest risk nodes in the grid. Step 2 deploys IoT sensors onto those assets. Steps 3 and 4 train the AI models, scaling automated work orders across the entire public works portfolio. By catching equipment degradation this early, a city can perform a planned repair for as little as 1/9 the cost of an emergency failure response. Facility managers use these dashboards to track documented cost avoidance. This data provides the transparency needed to justify capital budget requests to government officials. Restorative engineering provides the digital logic required for physical mechanics to save a city millions. It ensures that a single, timely wrench turn replaces the disaster of an infrastructure collapse.